Welcome back everyone. In our previous lecture, we explored the physical origin of Raman scattering and learned how molecular symmetry affects Raman intensity through the depolarization ratio. Today, we are going to take a major step deeper into quantum mechanics of Raman spectroscopy. We will explore two extremely important topics: pure rotational Raman spectra and pure vibrational Raman spectra. These spectra allows us to determine incredibly precise molecular properties such as bond lengths, moments of inertia, rotational constant, and vibrational energy spacings. In many ways, Raman spectroscopy becomes a direct window into molecular mechanics. Let us begin with pure rotational Raman spectra. In pure rotational Raman spectroscopy, the molecule undergoes transitions only between rotational energy levels. There is no vibrational transition and no electronic transition. Only rotation changes. This types of spectrum is especially important for diatomic molecules, linear molecules, and gas phase molecular analysis. To understand rotational Raman spectrum, we model the molecule as a rigid rotor. This is one of the most important approximations in molecular quantum mechanics. Imagine two atoms connected by a perfectly rigid bond. The bond length does not change. The molecule simply rotates in a space about its center of mass. Because angular momentum is quantized, the rotational energy levels are also quantized. The allowed rotational energies are given by Ej is equal to Bj into j plus 1, where j is the rotational quantum number and b is the rotational constant. The rotational constant depends directly on the molecular's moment of inertia, and the moment of inertia depends upon atomic mass and bond length. This means the rotational spectroscopy gives us direct structural information. By measuring rotational transitions, we can calculate bond length and extraordinary precision. Now, not every molecule can produce a rotational Raman spectrum. For rotational Raman activity, the molecule must possess anisotropic polarizability. Anisotropic means direction dependent. As the molecule rotates, its electron cloud must present different polarizabilities in different orientations. For example, linear molecules like N2 and O2 are rotational Raman active, even though they are microwave inactive. This is one of the Raman spectroscopy's major strength. Now let us discuss the quantum mechanical selection rules in microwave spectroscopy. In rotational, selection rule is delta J is equal to plus minus 1, but Raman spectroscopy is a different. For rotational Raman scattering, the selection rules for the selection rule becomes delta J is equal to 0 comma plus minus 2. This is extremely important. Let us interpret these transitions physically. If delta J is equal to 0, there is no change in rotational energy. This produces Rayleigh scattering, elastic scattering. The scattered photons remains the same energy as that of incident photon. If delta J is equal to plus 2, the molecule gains rotational energy, the photon loses energy. This generates Stokes-Raman lines. If delta J is equal to minus 2, the molecule loses rotational energy, the photon gains energy. This generates anti-Stokes-Raman lines. Now, let us calculate the energy shift. This is where the mathematics becomes beautifully elegant. For rotational transitions, uh, J tends to plus 2, the energy difference becomes delta is equal to B into 4J plus 6. This means Raman shifted Stokes photon has energy h nu naught minus B into 4J plus 6, where nu naught is the excitation frequency. Anti-Stokes energy, similarly, for the anti-Stokes transition, J tends to minus 2, the energy becomes h nu naught plus B into 4J plus 6. Notice something remarkable. The energy shifts are perfectly symmetric around the Rayleigh line. That means Raman spectrum is symmetric about the central excitation frequency. Now let us calculate the spacing between the successive Raman lines. Suppose we compare two neighboring Stokes transitions, we subtract their energies, everything simplifies beautifully. The spacing becomes 4B exactly. This is enormously important experimentally, because if we measure the spacing between Raman lines, we immediately obtain the rotational constant B. Rotational constant B. And once we know, we can determine moment of inertia, bond length, and molecular symmetry. Look carefully at the predicted rotational Raman spectrum. At the center sits the massive Rayleigh line, and the first Stokes and anti-Stokes lines appear at 6B from the center. After that, every neighboring line is separated by 4B. This equally spaced pattern is one of the signatures of the rotational Raman spectroscopy. There is another beautiful insight here. In microwave rotational spectroscopy, line spacing is equal to 2B, but in Raman rotational spectroscopy, the spacing equals 4B, because the selection rule changed from delta J is equal to plus minus 1 to delta J is equal to plus minus 2. Rotational Raman spectroscopy is extremely useful for molecules that are nonpolar, symmetric, or microwave inactive. For example, N2O2, H2, and Cl2. These molecules cannot produce microwave rotational spectra, but they can produce beautiful Raman rotational spectra. Now let us move upward in energy and discuss pure vibrational Raman spectra. Instead of rotational transitions, we now focus on vibrational transitions. We begin to the harmonic oscillator approximation. The vibrational energies are given by as shown in the slides, where nu is equal to 0, 1, 2, 3 is the vibrational quantum number. In the harmonic approximation, the molecule behaves like a perfect spring. The energy levels are equally spaced. However, real molecules are not perfectly harmonic. Real molecular bonds eventually weaken and dissociate. Therefore, real molecules behave as a harmonic oscillators. Anharmonic oscillators. So when we include unharmonicity, the selection rules expanded. In infrared spectroscopy, the strongest transition is usually delta nu is equal to plus minus 1. But Raman spectroscopy allows delta nu is equal to plus minus 1, plus minus 2, plus minus 3, and so on. These additional transitions produce overtones and higher order Raman bands. Now, practically speaking, most molecules at room temperature occupy the vibrational ground state. Therefore, the dominant transition is delta nu is equal to changes from delta nu is equal to 0 to nu is equal to 0 to nu is equal to 1. This is called the fundamental vibrational Raman transition. The Raman shift directly equals the vibrational frequency of the molecule. Therefore, the vibrational Raman spectrum provides bond strength information, functional group identification, and molecular structural analysis. Now, things become even more interesting for light dynamic diatomic molecules in the gas phase. The vibrational spectrum is not a single line. Instead, each vibrational transition contains rotational fine structure. This produces a combined spectrum, a vibrational rotational Raman spectrum. The selection rules the selection rules are the, the selection rules remain delta J is equal to 0, comma plus minus 2, but now they occur simultaneously with the rotational vibrational transitions. This creates three important spectral branches, and this is where the Raman spectroscopy differs dramatically from IR spectroscopy. In IR spectroscopy, we usually observe P branch and R branch. The Q branch is usually forbidden for diatomic molecules in IR spectroscopy, but Raman spectroscopy allows three branches. If delta J is equal to 0, we obtain the Q branch. This appears as a sharp, intense central line. If delta is equal to plus 2, we obtain the S branch. These are the Stokes side rotational transitions. If delta J is equal to minus 2, we obtain O branch. These appear opposite side of the spectrum. Why Raman spectra are so rich? Because Raman spectroscopy includes rotational, vibrational, and polarization information simultaneously. The spectra contains enormous structural detail. From a single Raman spectrum, we can determine bond length, bond strength, molecular symmetry, rotational constant, vibrational frequencies, and even temperature distribution. These principles are fundamental in molecular physics, atmospherical spectroscopy, astrophysics, and gas analysis, and many other chemical characterization. Modern Raman systems can resolve these rotational structures using high resolution lasers, Fabry-Perot interferometers, and CCD-based spectrometers. So what we have learned today. We explored the pure rotational Raman spectra using the rigid rotor model. We derived the rotational energy equation and learned that the Raman rotational selection rule, that is delta J is equal to 0 comma plus minus 2. We showed that Raman rotational lines are spaced by 4b, allowing direct calculation of molecular bond strength. We then moved to pure vibrational Raman spectra using harmonic and anharmonic oscillator models. Finally, we examined vibrational rotational fine structure and introduced the O, Q, and S branches. In our next and final lecture of this unit, we'll leave the quantum mechanics behind and step into laboratory once again. We'll explore modern Raman instrumentation, laser systems, detectors, sample methods, and real-world Raman applications in chemistry, biology, medicine, and material science. Thank you for watching. I will see you in the final lecture.